The central riddle of reconnection that's being investigated by MMS is the fact that somehow in space, where in fact the conductivity is like your copper wire, it's very, very high. There's a process that converts magnetic energy to particle energy. You know that in a process like a resistor. A resistor converts electromagnetic energy to the heat of the resistor. And it does it because it has a finite resistance. But in a wire, there's not much dissipation. So what we're really interested in is turns out very, very thin regions in space. They have currents, like in the wires, and also electric fields in such a way that there's a net electric field that changes magnetic energy into heat or particle or kinetic energy. Fortunately, these regions that we know from many astrophysical observations from the sun to astrophysics to around the Earth are very, very thin. They're very, very thin currents. What we're looking for, as illustrated in this slide, is very thin current layers such that, illustrated by this yellow and blue line, what's called the fusion regions, where there's a finite resistivity, not like a resistivity, but a finite electric field that converts electromagnetic energy to particle kinetic energy. What actually happens in this picture is plasma flows into these regions from below and above, and then gets jetted out at very fast speeds off to the left and the right through this region, flowing through either these regions here, which are called separatories, that are associated with this geometry, or through this diffusion region. And to measure these, as seen on the right-hand side, we have very, very thin layers. This layer may not seem thin to the average person, but it's 10 kilometers. Unfortunately, out in space, this current layer moves by the spacecraft at 100 kilometers per second. So all the physics in MMS has to do with trying to capture that electric field in a very short time period of a tenth of a second. So this is a computer simulation of one of these diffusion regions that we believe exists around the Earth, on the Sun, astrophysical situations, in which what we're plotting here is a color-coded plot of essentially what is called E plus V cross B, which is essentially the electric field in the frame of reference of the plasma. And it's this electric field in that frame that essentially breaks the connection of magnetic fields, as is seen in this picture, as the magnetic fields flow in from the top and from the bottom, and then reconnect in this region called the diffusion region, or the X-line region. And then these magnetic field lines are formed, and they are responsible for accelerating the plasma rapidly to the left and the right. And we do observe these fast-flowing plasma regions to the right, to the left of the right, called the jets, reconnection jets, which tell us that something like this must be happening. We do observe this topology. What we have not been able to observe is the very thin dynamics in this region. And all the previous theory says that such reconnection, such reconnecting of fields, such conversion of magnetic energy to plasma energy simply cannot go on in a plasma which is very much like a superconductor. All the fields are frozen in a superconductor, and it cannot go on. So we don't know what's actually happening in this very thin region. And MMS is designed to try to capture the physics in this region. Unfortunately, that region goes by the spacecraft at about 100 kilometers per second. And this region, we believe, is of order 10 kilometers in width, so that we see it for about a tenth of a second. So that means that we have to have extremely high time resolution to make all the electric field measurements and flow measurements in this region. And at the same time, we have to keep this data and somehow send it down to the ground. Now, the amount of data that generates far exceeds what we're able to get to the ground. So there's a big challenge is to identify this region in our data somehow automatically or via a very quick analysis on the ground and send that data to the ground.